Good morning. Good morning. A very warm welcome to all of you to this program organized by Breakthrough Science Society. My name is T.K. Shahjahan and I am a volunteer and a state committee member of the Breakthrough Science Society. I also teach physics in the National Institute for Technology, Karnataka School of Science. So Breakthrough Science Society, for those of you who are new to our program, is a voluntary science organization working in about 20 states in India. We have volunteers across the length and breadth of the country. We believe science should be for man, science should be for society, and science should guide our thinking. With this aim in mind, we organize various programs, we organize talks, we organize seminars, symposia, we arrange demonstrations and street plays, and we publish books and magazines. So we publish in many major Indian languages, including English, Hindi, Malayalam, Bengali, Kannada, and so on. We publish a journal and we publish various books on various topics. So I request you to visit our webpage. We'll get an overview of our activities and our publications there. So today's program about Professor Weinberg, the life and work of Professor Steven Weinberg, who passed away a month ago. Professor Steven Weinberg, as many of you know, had received a Nobel Prize in Physics for his work in unifying fundamental forces in nature. Apart from his research, he was a great educator, speaker, and he had a wide range of interests. His books are extremely popular. His three-volume book on field theory is considered to be a Bible. His book called The First 3 Minutes is very popular. And his latest book, recent book called To Understand the World, is a history of man's intellectual attempt to understand the world and explain it from the Greek antiquity to the modern science. And Professor Sunil Mukhi will be talking more about Professor Weinberg's life and work. Professor Sunil Mukhi is a very apt person to talk about Professor Weinberg. He shares his research interests, field theory, string theory, and particle physics. Professor Sunil Mukhi also has a wide range of interests. I used to follow his very entertaining and very interesting blog called Tandujal a decade ago. And so I am very honored and pleased to have him as a speaker with us today. So I welcome Professor Sunil Mukhi to this program, and I welcome all of you to this program. And I request you to, if you have any questions, comments, or suggestions during the program, please type them into the chat window in YouTube or Zoom. So we'll discuss them after the talk. With these a few words, I request Professor Sunil Mukhi to start the session. Welcome, sir.
Thank you very much, Shahjahan. I hope you and everyone can hear me well.
Yes, sir.
Good, that's great. And I'd like to thank the Breakthrough Science Society for their kind invitation, and also all of you for sparing a Sunday morning to come and hear me talk about Weinberg. Let me share my screen first, and then a little bit give you an idea what how I'll be doing the talk. So I hope you can see this.
Yes, sir.
Okay. I did not personally know Steven Weinberg, but I only once in my life attended a lecture given by him in Venice, of all places, in Italy in 1982 or 83. And of course, it was very impressive, but it's also very long ago. But then through my PhD and through my entire career, I have followed his papers. Sometimes I have read them when they newly came out. But always I have referred to them and also to the textbooks that he wrote, and also read some of the, not all, but some of the popular books that he wrote. And so I'll try to make a kind of narrative about this extraordinary person, and I hope you'll find it interesting. And in between, I'll pause and see if there are questions in the chat window, and which I'll be happy to answer. Otherwise, I'll also answer questions after the lecture. So I'll start now. And just one disclaimer before I get any further is that this presentation does use images, and even there are some embedded videos and quotes. I didn't check if they are in the public domain. So they are used under a doctrine which exists in US called fair use for the purpose of delivering a lecture to basically a private audience. All right, so let's move on. Good. So I'll start with a quote from Weinberg himself, which says, "Scientific explanation is a mode of behavior that gives us pleasure, like love or art." And in some ways, that should set the tone for what we are going to talk about. Now, what I'll do is to let you hear about this person, first of all, from himself. And what I have here is just about a 1 minute or 1.5 minute clip from an interview he gave to Bill Moyers in 1990. Here you see a relatively young Steven Weinberg. Later, we'll see some more videos where he was quite a lot more senior. But this video is this clip is nice because he's basically asked, what is it that you want to do? And he explains it in very beautiful terms.
What is it you want to know about the universe? I just want to know one thing, which is why things are the way they are. I think that we've come a long way. You know, if you ask any ordinary question about everyday things, why is the sky blue? Why is water wet? We actually know the answer. We, meaning the whole body of physicists and chemists and biologists, we know the answer to these things. Then you ask, why are those things the way they are? And we've come a long way. We now have a picture that underlies atomic physics in terms of the properties of elementary particles. It's sometimes called the Standard Model, which is a way of saying we all believe it and use it without being absolutely sure of anything. And then you ask, why is that true? Well, that's what I want to do. I want to trace these chains of why down to their roots.
Okay, so that's Weinberg telling us what he wants to do. He wants to understand the why questions. Let me now start by summarizing briefly his career. So he was born in New York City in 1933. A very interesting fact is that he went to a high school called the Bronx High School of Science, which has produced, besides himself, a number of eminent scientists, including 6 physics Nobel laureates other than himself, one of whom was his batchmate. So let's go through the list. Leon Cooper of Cooper pairs and BCS theory studied at that school. Sheldon Glashow was actually not only in that school, but he was in Weinberg's class. So they were classmates, and they eventually shared the Nobel Prize. Roy Glauber, who got a prize for optical coherence, and then Russell Hulse, who is part of the team Hulse-Taylor, who found the first binary pulsar. Hugh Politzer, who found this asymptotic freedom property of the interquark force in strong interactions and got a Nobel Prize for that. And Melvin Schwartz for the muon neutrino. And these are 6 Nobel Prizes in physics. There was also a Nobel Prize in chemistry, I think, that I didn't list, from the same school. And then there are also other famous students, namely Leonard Susskind, who is one of the early proposers of string theory. And of course, a person that surely you have all heard about, Neil deGrasse Tyson. He also studied in this school. Bronx is a district or a borough in the northern part of New York City. So there's something remarkable in that which we should think about. How does a school, like maybe the school attracts brilliant people or it makes them brilliant? Maybe it does both. Anyway, so what are his degrees? Well, after high school, he went to Cornell for his BSc and Princeton for a PhD, which it just took 3 short years. And he had his PhD at the age of 24. Postdoctoral fellowships, he spent some time at Columbia and again in New York City, and then he moved to Berkeley. And in Berkeley, after a year or some time as a postdoctoral fellow, they eventually offered him a faculty position, and he spent 6 years or 7 years in Berkeley as a faculty member. But then after that, so during that period, there was a very important event. He visited Imperial College in London in 1962. Now, I can't figure out whether it was for the summer or for a longer period, But it was a visit at the, apparently at the invitation of Abdus Salam, and they actually collaborated during that visit, and that was to have an important impact on his professional career. Then he joined Harvard, according to Wikipedia, in 1966. But the puzzling thing is that, and then, okay, 66 to 82, which is 16 years. And after that, from 1982, he moved to the University of Texas at Austin, which is a state university. Harvard is, of course, a very rich private university, and Texas, Austin is a state university, and it's more modern, as you can see by comparing the buildings. But again, there was an interesting fact that from Harvard, or maybe either before or after Harvard, he spent 1 year at MIT, which is essentially walking distance, half an hour walk from Harvard. I've done it myself. But he went to MIT, also in Boston. And in fact, you'll see that two of his important papers, one is when he was in Imperial College, and one is the one when he was at MIT in 1967. Curiously, that paper has no mention of Harvard at all. That's why I'm not sure of this data about 1966. Maybe he was hunting to see which position he can get or which position he prefers to take, but he eventually settled on Harvard. And certainly during the time I was doing my PhD, which is late 70s till 81, he was in Harvard. And soon after that, he moved and spent the rest of his life in Texas. Texas will come back later in this talk because there were some interesting incidents connected with him being there. Now, Weinberg was, of course, a prolific researcher with around 180 publications. That number is actually small in other fields of research. After all, he was publishing until essentially this year, 2021, and he turned 88 this year. Essentially, all his papers are on theoretical high-energy physics and cosmology, and they go around the concepts of quantum field theory, particle physics, how the experimental discoveries of particles can make sense in the language of quantum fields, and how the internal structure of quantum field theory itself is highly consistent and highly predictive. And then slowly but surely he drifted towards cosmology, which is an application of particle physics to the early universe, and somehow, and of course, of gravity. Yeah, somebody is writing on the screen. This is a common problem. Organizers need to stop annotation.
Yes, sir.
And also delete this writing if you can. Anyway, I'll continue. So you should stop both annotation and screen sharing for participants. So this is very irresponsible behavior, but it's quite common also. All right, good. Now, Weinberg's first paper was written in 1956 at the age of 23. And it's not that remarkable a paper, and I won't go into it. I can't review 180 papers in this talk, but it was it showed that he is getting into a certain field. He didn't arrive with a bang with a brilliant paper which established him. But in this period, 1956 to 62, he wrote several papers which started to establish himself as a solid researcher. And some of them, by the way, did very well. For example, they provided proofs of theorems in quantum field theory originally done by Dyson and Salam. They understood them better and so on. So he was doing very good work, and a lot of it was single author. But after 62 and that visit to Imperial College is when his career really took off. So I've picked 3 research topics to discuss in this talk. One is the Electroweak theory, for which contribution he got a Nobel Prize. The second is Axions, which I'll be a little more brief. And the third is the cosmological constant or vacuum energy density of the universe. Thereafter, once I'm done talking about these 3 technical topics, I'll briefly discuss his textbooks, his popular books and articles, and also his public advocacy, his public statements about issues that he passionately believed, some of which might seem even now quite controversial, and it's worth it for you to hear about them. Let me take a quick look at the chat. Okay, it's only good mornings. Very good. Okay, let's move on. Now this annotation has to be removed. So I'm unsharing my screen and I'm sharing it again. And I hope this, because this, I cannot keep giving a talk with this scribble, irresponsible scribble on it. Okay, hopefully this works. Good. So I'll start with electroweak theory. Let me say that it's not easy to explain any of his research to a general audience. I assume that many of you are, of course, interested in physics. You have read about physics, at least from Wikipedia and internet sources. But I won't assume that you know the advanced concepts which I used here. So, well, as we go along, I'll use some things, some words which you may understand, some which you won't understand, some which are in between where you may have a vague idea, and it's perfectly all right. Once you have some vague idea what's going on and why things are interesting, you are very welcome to go and look at the literature yourself and slowly learn the material you need to understand things better. So that's the spirit of this discussion. Now, by the late 1950s, researchers were seeking the theory underlying what are called the weak interactions. So this was a new force of nature discovered at that time, beyond electromagnetism and beyond gravitation. In fact, two types of nuclear interactions, weak and strong, were discovered in the 20th century, mid-20th century. And we are going to focus on the weak interactions because that's really where Weinberg first made his mark. Now, weak interactions are the reason for nuclear beta decay, and they are also the reason for decay of other particles like muons, which fall in the family of leptons. So electrons and muons and tau leptons, these three are the charged leptons, and then there are also neutrinos, which are also leptons. And leptons are very important to this talk because they are the central theme of Weinberg's Nobel Prize winning work. Now, both nuclear beta decay and muon decay give rise to neutrinos. And this is one reason for us to immediately realize that they must be weak decays. That is, they are decays caused by the weak interactions. Whenever you see neutrinos in a process, it's a weak process because neutrinos don't undergo any other type of process. Okay. Now, electromagnetic interactions were well understood by the late 1950s, thanks to quantum electrodynamics. The seminal work of Feynman, Schwinger, and Tomonaga. Although the Nobel Prize was quite late in 1965, apparently, even I was surprised by that. But the work was done much earlier, and so electromagnetic interactions were considered well understood. And for that, this theory, quantum electrodynamics, was the prototype of quantum field theory. And all quantum field theory, in some sense, is based on the intuition provided by these early works in quantum electrodynamics. But interactions like muon decay were definitely not electromagnetic. They were, in fact, weak interactions. And moreover, they were known to violate parity, which is left-right symmetry. This was discovered by Li and Yang in 1956. And as I said already a couple of times, weak interactions typically give rise to neutrinos. So the muon, which comes to us from cosmic rays, decays to one, each muon decays to an electron and two types of neutrinos. Actually, one of them is an anti-neutrino, but I've denoted both of them as nu, which is for neutrino, the Greek symbol nu. Okay, so this is what people wanted to understand. Now, Enrico Fermi had the first sort of concrete idea how to model this. He said, well, actually, he didn't say what I'm about to say. He said the analogous thing for beta decay, which is decay of a neutron in the nucleus. But it turns out it's very easy to generalize to the decay of muons. So he said, well, there's a 4-point vertex, which you see in this figure. And time in this figure, time goes upwards. So the muon comes in, and then at one point, it decays into a muon-type neutrino, into an electron, and into an electron-type antineutrino. All this became known a little bit later very clearly. But basically, this is Fermi's picture. It's just a picture, but of course, there was a formula with that, okay? And the formula was called a current-current interaction. I don't have time to go into it in more detail. But the basic idea was that nothing else happens. The muon simply at one point, as a quantum process, decides to split into 3 particles, and these are the 3 particles. And he gave a probability for that. from which you can actually get reasonable experimental results which agree with experiment. But partly by analogy with electrodynamics and partly for another reason that I'll explain soon, researchers right from the 1950s and starting, I think, with Julian Schwinger, had come to believe that the real picture of muon decay is not the upper one of Fermi, but it's this lower one. I don't know if you can see my cursor going around the figure. I hope you can. And in this picture, the muon first splits into a neutrino and a W particle, which was not known at the time. And then the W particle splits into an electron and antineutrino. So it's like a two-step process with an intermediate particle. And that particle came to be known as IVB, intermediate vector boson, or W boson. It was also called Z before. It was a bit confusing in those times. Now we know that there's a W and there's a Z, but anyway, notation is not so important. An intermediate weak boson. By the way, W presumably was for weak, but as people joked later, possibly it was for Weinberg, who was going to explain this better. Okay, so this hypothetical particle is a vector boson. Vector means it has a spin 1 in units of h bar, and it communicates the weak force in a similar way that the photon communicates the electromagnetic force. And it's not surprising that Schwinger would think of this diagram because he had just participated in developing electrodynamics, where the photon plays a similar role in processes to this proposed role for a W particle. So this was the status, particularly Schwinger's paper in 1957 put forward this proposal. Now, it wasn't just by analogy. It was not like people said, well, if there's a photon, there should also be a W boson for weak interactions. The fact is that Fermi's theory came with a fundamental inconsistency built into it, namely that at high energies, it would inevitably break down. It had a mathematical structure, which in quantum field theory, we understand very clearly now, doesn't survive to high energies. It violates bounds on these processes that are theoretical in nature, and basically the theory becomes inconsistent. And inconsistency of quantum field theory is a very important theme running through essentially all major studies of quantum field theory. So one had to save Fermi's theory, and intermediate force carriers, it was known, had the potential to save this by replacing a 4-point interaction by 2 3-point interactions. Somehow, when you have lower point interactions, it works better. Now, Schwinger also observed that this W must have a mass, unlike the photon, which is massless. And the reason is that the range of the force is inversely proportional to the mass of the particle. Because the photon is massless, light is able to reach us from distant stars and galaxies. But if it had a mass, then the light would just intrinsically be attenuated at a distance of order 1 over that mass. And weak interactions are known to be short range, which means the mass of the weak force carrier, if there is one, must be significant. Now, that's the experimental reason. Now, theoretically, the photon is exactly massless due to a certain symmetry of Maxwell's equations, which many college students would study, called gauge invariance, which basically says I can take the scalar and vector potentials and shift them by a certain amount in a certain way together, such that the electric and magnetic fields don't change. Now, this invariance is not just a property of Maxwell's equations, but it's a needed property, without which the equations or without which the photon would not remain massless, but quantum corrections would give it a mass. This symmetry is needed to fix its mass in some sense. The symmetry is also needed for the high energy consistency of quantum electrodynamics itself. Okay. Now, if we expect the weak interaction theory to be similar to quantum electrodynamics, then we would like it to have gauge invariance, which would be needed for its high energy consistency. But that invariance would have made the W boson massless. And if it's massless, then the weak interactions become long range, which disagrees with experiment. So somehow these weak force carriers should not have this gauge invariance type of symmetry, or maybe they have it, but it's approximate in some way. These were kind of thoughts that people were throwing around at that time. And the reason they were throwing these thoughts around is that if you abandon gauge symmetry altogether, then consistency is lost at high energies again. So quantum field theory has this tendency to lose consistency unless certain things are in place, and gauge invariance for vector bosons is one of them. That lesson has survived until today. At that time, it was a bit of a speculation. A lot of things happened later, which made it clear that, these statements are all correct. Okay, and now we go to 1960 and Dr. Sheldon Glashow. He was at Harvard actually, and this isn't a talk about him, so I don't have more details about him. But he was visiting Copenhagen at the invitation of Niels and Age Bohr actually in 1960. And during that time, he wrote this rather remarkable paper. And in this paper, he proposed a model in which both weak and electromagnetic interactions were accounted for. So you could say it was like a generalization of quantum electrodynamics to include weak interactions. And in his model, there was a W boson, which was part of a triplet of 3 particles. And there was an additional force carrier called the Z or Z boson. Okay, so there were 4 particles, and one of these 4 was identified with the photon, and 3 would be new. And actually, this paper is remarkably close to the final answer. This was Glashow's main contribution to the final theory of electromagnetic and weak interactions, which would go on to get the Nobel Prize for him and Weinberg and Abdus Salam. But the nice thing is that Glashow, the interesting thing is that Glashow came up with this idea first and alone. The problem was that his force carriers didn't have, there was no explanation for their mass. And if you agreed that, well, because there's mass, there can't be gauge invariance, then as I've told you, the theory would break down at high energies. So it couldn't be the fundamental theory he was looking for. And today we know that although Glashow's model had essentially almost all the ingredients of the final electroweak theory, by itself, it's not consistent and it breaks down at high energies. It was basically missing one thing. Okay, so now let's come back to Weinberg. I told you that he visited Imperial College in 1962, and during that visit, he wrote a paper with Abdus Salam, who was there, and Jeffrey Goldstone. Now, Goldstone had already made a conjecture that in quantum field theory, I'll read out the words and then I'll try to explain. Spontaneously broken continuous symmetries lead to massless, spinless bosons. It's a long sentence, and all these things may or may not be familiar. Hopefully, continuous symmetries is a familiar concept. They are transformations on the fields of quantum field theory, like the electric and magnetic field or vector potential. If these break not explicitly, but they are broken spontaneously, which I'm about to explain, then they lead to a new kind of particle or a new kind of excitation in nature, which is a boson, a bosonic particle, which has no spin. That should be easy to understand, but also has no mass. Okay, now let me show you from this bowl picture. I hope this picture is clear. It's like an inverted bowl in the middle. And the mechanical analogy is that I could place a red marble. I could start by placing it at the top of this hill in the center. Now, that's not a stable place. If this bowl was made of glass, as it looks, if you put a marble at the center, it won't stay there. It will roll down. But which way it rolls down will be random. There's no preferred way for it to roll down because the bowl is perfectly symmetric under rotations, but still we know it rolls down. Okay, and once it rolls down, it's reached a minimum over here, and there's a circle of minimum points over here. It's reached one of those points. But now notice that this marble doesn't need much energy to roll along the circle. Okay, that's the analog of a massless particle. So the fact that this symmetry is broken is the fact that if a particle is placed at the center, this turning point of this hill is unstable because it's a maximum, not a minimum. So it rolls. And once that happens, and once it's reached its broken symmetry equilibrium point, then it has freedom to move along a circle at very minimal cost in energy. And that's also because of the symmetry. That's why the circle, it's like a flat direction. You just give it a little nudge and it will roll. And this is basically the mechanical version of Goldstone's theorem. Now, massless, this is all fine. This is a true theorem in this bowl problem. But in quantum field theory, the analogous theorem says there should be massless particles with zero spin, which undergo weak interactions. And no such particles are seen in nature, and they are pretty strong bounds on their possible existence. So this theorem was a little bit of a dampener, saying that spontaneously broken type symmetries are basically ruled out. We can't have those in nature. But they didn't apply their theorem to gauge symmetries. They applied them to what we call ordinary continuous symmetries, and gauge theories turned out to be a loophole. Now something else happened. In 1965, by this time, people were seriously worrying about this spontaneously broken symmetry problem and also about weak interactions. And Peter Higgs, along with Engler and Brout, came up with a mechanism to address exactly this puzzle. And what was their mechanism? They started with a gauge symmetry, but they made it spontaneously broken, something like this bowl. But it was a gauge symmetry, and therefore there was some vector particle, spin 1 particle, undergoing this gauge symmetry, which was analogous to a photon. Now, naively, if you believe Goldstone, Salam, Weinberg paper, the system will produce these unwanted massless, spinless bosons. They were conjectured earlier by Goldstone. But these authors showed that in presence of gauge symmetry, this does not happen. Instead, by a clever change of variables, and a very simple one, these are, by the way, quite simple papers to read, they only involve classical fields. Via a change of variables, the Goldstone mode disappears and it's replaced by a massive vector boson. That means a spin 1 boson, which has a mass. And that's wonderful because that's exactly what we've been looking for in weak interactions. Now, if Higgs, Engler, and Brout had been working on the kind of things that Glashow did in 1960, and if they had been super smart, they could have come up with the next step, which is make the realistic model of nature in which this Higgs mechanism, along with Glashow's proposal, all work together. But they didn't do that. They simply wrote a theory paper saying spontaneously broken gauge symmetry both gives mass to false carriers and removes this massless particle, which is in conflict with experiment. So the theories start looking much better. So this family of spontaneously broken gauge theories was elevated by these papers in 65 to potential theoretical frameworks for the theory of weak interactions in particular. But of course, not everyone believed this whole idea, this whole set of ideas. And now comes in Weinberg. In 1967, from MIT, he wrote a paper, single author paper called A Model of Leptons. Now it's very interesting. The paper is exactly 3 pages long. As you can see here, it is page 1264 to page 1266 in FISREV letters. Today it has 13,262 citations. That's actually much less than the number of people who use it, because most of the time it's so well known that we don't even need to mention his name in our papers. Now, in this 3-page paper, he published a formula for the potential model or theory that synthesized the ideas of Schwinger, of Li and Yang, I didn't mention, of Feynman-Gell-Mann, I also didn't mention, on parity violation, of Glashow, of Goldstone, and of Higgs, Engler, and Brout. And this is what you really see, that it's not that Weinberg out of the blue had some illumination and suddenly wrote some theory that people were baffled. He believed everything that had been written by all these people, and in his mind, he was able to collect it all and say, this is what those results are saying. He also kept close contact with experiment, and so he knew what things are experimentally possible and not possible. And he modestly called the theory a model of leptons, but actually, more or less with few changes, minor changes, that is the theory of leptons as we know it today. Now, its reliance on Glashow's work was phenomenal. So actually, Glashow has every reason to be part of this Nobel Prize, but could have also involved Schwinger or Higgs or a lot of other people, Goldstone. And anyway, that's not how it worked. Abdus Salam did his own independent investigations at Imperial. And again, this talk is not about him, but he also shared in this prize. Okay, so here are some lines from Weinberg's talk. Unfortunately, because this Zoom bar is covering, yeah, okay, I can move the bar. Okay, this is the opening lines of his paper. Leptons interact only with photons and with the intermediate bosons that presumably mediate weak interactions. What could be more natural than to unite these spin-1 bosons into a multiplet of gauge fields? You see here that unification is in Weinberg's mind. It was also in Glashow's mind, because the goal was to explain weak interactions. Electromagnetic was understood. But both of these people and Salam realized that actually weak and electromagnetic are manifestations of one common set of interactions. And that's why the resulting theory is called the unified electroweak theory. It doesn't include strong interactions, doesn't include gravitation, but 2 out of the 4 interactions in nature are unified. And people have said since then that it's almost as dramatic as unifying electricity and magnetism, which used to be 2 separate subjects, into electromagnetism. So this is a modern day unification. And this is how he described his note. He said it will describe a model in which symmetry between electromagnetic and weak interactions is spontaneously broken, but Goldstone bosons are avoided by introducing the photon and intermediate boson fields as gauge fields. So this is basically Higgs-Englert-Brout theorem, that once you have gauge symmetry, Goldstone bosons get avoided. And he said the model may be renormalizable. This is our word for consistent at high energies, and he couldn't prove it. And in fact, it was proved many years later by 't Hooft and Weltman, who got a separate Nobel Prize for proving that mathematical consistency. And here, if you like, is one of the formulae. What I like about it so much is that this notation doesn't need anyone to think, oh, how are they using notation in 1967? It's exactly this notation which you'll find in a book, even if that book is written on the subject today. It's really modern in that way. Okay, good. So the model unifies the weak and electromagnetic interaction. And a new thing, it also uses the Higgs to give mass to other particles. Now, this has to do with parity violation, and it would be too long a discussion to go into here. But you may have heard this statement that Higgs gives mass to every particle. This was Weinberg's paper. It was really not there before that. And it's crucially because of the structure of Weinberg's model, about which the details you'll have to learn whenever you learn quantum field theory. Now, the paper of Weinberg predicted 4 particles not seen before. That's a very bold thing to do. 3 of them were called W plus and minus and Z. These were the vector bosons, which are the carriers of weak interactions. They were originally from Glashow's paper, but there was a slight difference in how they are described in Weinberg's paper. And exactly the one that Weinberg described was detected indirectly in 1973, and all 3, W plus, minus, and Z, were directly discovered in 1983. It had to wait for accelerators to be built. But this indirect detection was good enough for the Nobel Committee. Since this happened in 73, they gave the Nobel Prize to Glashow, Salam, and Weinberg in 1979, even though these bosons had not been directly discovered. And that's quite striking. The 4th particle was the Higgs boson. Now, this was a spinless boson, but not a massless one. And it was a kind of side effect, if you like, of the Higgs-Englert-Brout mechanism. And this had to wait a much longer time because it's just more difficult. It's not that heavy compared to the others. So these are in the range of 80 to 90 GeV, and this is 125 GeV. It's not all that much heavier, but the modes in which the Higgs is detected are different and needed much higher energy and better accelerators, and a gap of therefore 3 decades. And the Nobel Prize in Physics, as I said, in between went to these 3 gentlemen. Okay, now I'm halfway through my talk, and actually I'm also halfway, through the material. I'm also through the time, little more than half. Because this is sort of the thing for which Weinberg is justly famous. This is what he did. It's a 3-page paper. Of course, he wrote papers before that. He wrote papers after that. He wrote many more papers on the standard model, some of which we'll even be discussing. But this is the one I wanted to describe to you in some detail. So let's see what these, after SSB, why they become massless. So Gaurang, it's not that they become mass. After SSB, spontaneous symmetry breaking, there's a new massless mode in the theory. That's the Goldstone mode. That was Goldstone's theorem. It's not they become massless, but in the bowl picture, I tried to show you why that happens. The marble at the top is a marble in a potential. Being in a potential is like having a mass. But after spontaneous symmetry breaking, the marble rolls down, and now it's in a flat circle, not in a potential. There's no potential for it. It can roll freely. That's like becoming massless. Can we somehow predict how many Goldstone particles? Yes. Shaunak, thank you. Will be created by SSB. It absolutely depends on massless representations of the, not the little group, nothing to do with little group. It depends on it doesn't depend on massless representations of little group. It depends on the symmetry group, which is a Lie group like SU2 or SU3 or something. And it depends on the so-called vacuum expectation value that breaks the symmetry. So there are, Weinberg himself later in life, even much later, wrote long papers on patterns of symmetry breaking. So you can make many models. The one that was used in his paper was extremely simple. Arvindo, the 3-page paper by Weinberg, no, it's not really accessible if you have no QFT background. You absolutely need a QFT background. It's a QFT paper. And because it's in PhysRev Letters, which was a journal for dissemination of brief articles on major topics, it's very, very brief. It doesn't explain anything. It just tells you what the model is, and that's the end of the paper. It was the style in those days, and personally, I quite liked it. Gives you time to work it out, but it tells you what is the major result. Okay, let's move on. There are no more questions in the chat. Unless there's something the organizers want to ask from the YouTube, you can if you like. Otherwise, you can wait till the chat session.
Okay, so we'll take it up at the end.
Okay, fine. Okay, so axions. Now, a funny thing, in 1977, Weinberg proposed hypothetical particles that are in fact Goldstone bosons, namely they are massless, spinless particles. Bit ironic, considering 10 years earlier, he was trying to get rid of such particles. What he did, and independently we'll check also, their papers were submitted 1 week apart, showed that axions, that is a new type of particle, arise in a suitably generalized standard model where they play a certain role. They explain the reason why parity and time reversal invariance are not violated by strong interactions. If they were, then it would be much more visible than it is. Right now, parity violation in nature is very small because weak interactions are weak. If it was violated by strong interactions, then parity would be violated in everything, and that doesn't happen. So there needed to be an explanation. This is one of those why problems that Weinberg keeps talking about. Why is parity conserved in strong interactions? And they found that it will be conserved if there's a certain field theory which includes a particle, which is an axion, couples in a certain way, and its parameters are adjusted in a way that actually they don't contradict experiment. And to this day, people are searching for axions in astrophysical experiments because they are it's very compelling to believe that they do exist, but there's yet no proof. Now, interestingly, axions were detected as quasi-particles in topological insulators, and suddenly all the talk about axions has shifted to condensed matter physics, showing you what a unified subject quantum field theory is. The idea which so far didn't work in particle physics, nevertheless worked in condensed matter physics. That's really fascinating. And you can read all about axions and topological insulators. There's lots of stuff in the popular physics magazines and so on. So that was one. Now another problem, the cosmological constant. If you see, I've got one paper of Weinberg from 67, one from 77, and one from 87. This is just an accident. So he studied the vacuum energy density that is a natural part of Einstein's theory of relativity, and we know it as cosmological constant. In this year, it was not known whether this energy density is zero or non-zero. Observations had put an upper bound. Okay. Today, we also have a lower bound, and we actually know that it is this value, 10 to the minus 26 kilograms per meter cubed. But at that time, it was just an upper bound. So it's less than that. Maybe it could be zero. Okay. So this is the energy density and mass density units. You have to convert it using obviously mc squared of the universe as a whole. Weinberg wanted to explain these observations, why there should be an upper bound on the cosmological constant. The problem is, if we estimate this constant by saying it comes from quantum fluctuations of all fields in the standard model, you get an answer that is 10 to the 120 times bigger. Okay. Now, that's amazing. That's really bizarre. Okay. The measured value is 10 to the minus 120 times smaller than the value that you would naively predict. So something is wrong with the naive prediction. It's still a puzzle. That puzzle hasn't gone away. But in a 4-page paper, Weinberg brought out something called the anthropic principle, and he argued that this principle puts a sharp upper bound on the vacuum energy, and he calculated that bound. What is the anthropic principle? It says that fundamental constants take the values they do because those values allow for the emergence of life. And if they didn't, then we wouldn't be here to ask the question, the why questions. It's a very peculiar philosophical position, and Weinberg was not totally comfortable with it. Later, he wrote extensively about it, and you can read his thoughts on it in his popular books. But one thing is true, there is a kind of idea that maybe the universe has different branches where the parameters are different in different parts of the universe. And if that is so, then certainly we could not exist in those parts of the universe where the values of the parameters are not good for the emergence of life. So he said, well, let's take this as a guiding principle and see where it goes. But he hated abstract philosophy. I can, if you put this statement out in a general audience, people will love it because you can do a lot of idle chit chat about it. But he took it as a starting point for a calculation. And he showed that if this rho v is too large, then big gravitationally bound systems like stars and planets will not form. And if those don't form, then we don't get life. We need planets to live on and stars to give us heat to sustain life. Okay. And those would not form if rho is too large. And this leads to an upper bound. I was trying yesterday to estimate it from his calculations, but I couldn't finish that in time. So I'll leave it by saying that he found the vacuum energy should be of the same order as the actual mass density of the universe and not more. Okay, so it certainly can't be 10 to the 120 times more as the naive calculation gives. In fact, as the most recent measurements, I don't know the exact ones, but I looked up, it's starting from 1998, it became clear that about 2/3 of the energy of the universe is vacuum energy, and the remaining 1/3 is the matter that we know and dark matter. So the ratio of vacuum energy to actual matter is roughly rho v is twice of rho zero, which is non-zero, which he didn't know that at that time, 1987, but it certainly satisfies his bound. He also wrote a very influential review 2 years later on the entire subject of this cosmological constant with his work as a kind of small section in it. Okay, so with that, I'm done with talking about Weinberg's scientific contributions. What is technicolor theory? I don't believe I mentioned it, so I won't say so here. I don't have the time, unfortunately, but maybe if necessary, I'll come back to it in the discussion. Okay, So let's talk of textbooks. Weinberg was a masterful teacher and expositor of physics. Both in Harvard and in Austin, he was valued enormously for being a great teacher. And he was also a very good popularizer of science. Now, that's not true of all brilliant scientists, by the way. Many are poor teachers and many are poor public speakers. So there's no guarantee. Weinberg was very exceptional in this regard. Let me list his physics textbooks. 1972, Gravitation and Cosmology, set of 3 books on quantum theory of fields in 1995, 96, and 2000, Cosmology in 2008, lectures on quantum mechanics in 2012, lectures on astrophysics in 2019, and foundations of modern physics in 2021. You can see that as he got older, he wrote more books, which is quite a natural thing to do because your research slows down inevitably, and that's a good time to reflect and to collect all that you know. Now, these are all very impressive books, but I should say that they are not all necessarily the go-to textbook in the field. And I'll say a few words about gravitation and cosmology because I learned gravitation from it in the 1970s. And there are some unfortunate features in that book, which I will highlight for you now. Even quantum theory of fields, generally people agree that it's very good for a student who wants depth. It's not that useful for a student who wants something practical to get working with right away. The last book is very promising. It's a historical survey of what were the great events in modern physics and surveying each of them. I think this can be read by students who don't know QFT, or probably the last 3 actually. But I think this would be a very good book for a student to get a perspective. People often ask me, how do they get a perspective and decide whether they want to work in physics or not? I think this last book looks very, very promising. Okay. Now, the books are clear, lucid, and logical, no doubt about that. But they don't always follow the standard approach, and they were rephrased in his way of thinking. Now, his book, Gravitation and Cosmology, largely avoided Riemannian geometry, which is the basis of Einstein's approach. And let's see what Weinberg himself said. He said, too great an emphasis on geometry can only obscure the deep connections between gravitation and the rest of physics. So here Weinberg was basically being a particle physicist saying gravitation should be one more type of particle physics. Now, in some ways it is. After all, particle physics has electromagnetic waves, gravitation has gravitational waves, but in many other ways it's not. And what Weinberg missed in his book, though he could mention them very briefly, he was not able to go into them in detail, but today they are the most important things. He didn't talk about causality, about the way light cones orient or Penrose diagrams. He talked about black holes a little bit from an astrophysical perspective, but did not cover the classic works of Hawking and Penrose, which had been written in the late 60s and early 70s, and for which he apologized in the book. But unfortunately, for me at least, this book therefore followed a line which was Weinberg's line, and it's great for what it does, but unfortunately it left quite a lot of very important things undone, and which many of us had to catch up from other sources later. So that's one comment. Now let me turn to popular science books. He wrote a number of books, again increasing in recent years. So this one I have a copy, Discovery of Subatomic Particles, Dreams of a Final Theory I also have, and it really influenced me. It's a very good book on unification. Then these books, again, more books as he grew older. And finally, Third Thoughts, which is presumably comes after Second Thoughts. And I haven't read most of these, honestly, but it's a lot of books. And as you see, more and more in later years. Okay. All are good, all are highly recommended. These 2, which are pictured on the right, I can very strongly recommend from personal experience. The first 3 minutes, of course, is the most famous, and let me spend a few seconds on that. So here is the first 3 minutes, and here is the Tamil translation. So it's actually been translated into Tamil. I couldn't find out if it has been translated into more Indian languages. Actually, the Tamil translation is by M. Shiv Kumar from Hyderabad University, I believe, and who's actually right now giving a talk on Weinberg in Hyderabad University, online to Hyderabad University. I didn't know that. I just found out yesterday. In any case, It's a lucid introduction to, so I think it's that Shiv Kumar, I'm not 100% sure. It's a lucid introduction to modern cosmology for the reader who is not at home in either mathematics or physics. So this certainly students can go and read. In the introduction, he says, throughout most of the history of modern physics and astronomy, there simply has not existed an observational and theoretical foundation to build a history of the early universe. Now, in just the past decade, all this has changed. So this was the start of experimental cosmology of a level that was not dreamed of earlier. And that has gone very well since then up till today. And Weinberg has written about it in many research papers as well as in many other books and articles. But the book which was written in 1970s had to be revised in 93 because this is a rapidly evolving field. And even in 93, I don't know if the cosmological constant was very clear. Possibly it needed another revision. Now he's gone, so I don't know if that will happen or if he already did it in his lifetime. Okay, now let's turn to the last topic. It will only take 7 or 8 minutes, and now you'll be able to hear more from Weinberg and less from me. There were many causes he believed in. He has been open and fearless about his opinion on social issues. And let me say, he has also been fairly controversial to people who have strong opinions about the same issues. Now, I picked 3 which I think were very important. One for him. One was religion and science. One was science funding. And one was actually gun laws, which is the most recent and which intersected with his life only because he moved to Texas. If he had been in Harvard, in Massachusetts, which is a more liberal state, gun laws are very strict there and he would have had no problem. But in Texas, he actually ran into conflict with the law because he opposed guns, and we'll come to that in a few minutes. Okay. Now, let me immediately say that his opinions on religion and science are pretty controversial, or they could be. And if you're a person who doesn't like the kind of things he's going to say, you might want to tune out from this talk now, because on the next page, I will show him talking about his view of God and human beings. And it's not palatable to everybody. But this is Weinberg. It's a talk on Weinberg. I think I should show it. The first thing, of course, is in 2015, Times of India managed to score an online interview with him, presumably an email interview. I don't think he ever visited India, to my knowledge. But he said this very clearly. He said it's nonsense to say that modern science existed in ancient Greece or India. And he actually gave his reasons. Our predecessors in the ancient and medieval world often believed that scientific knowledge could be obtained by pure reason. Where they understood the importance of observation, it was passive, not the active manipulation of nature that is characteristic of modern experiment. Further, their theories of the physical world were often muddled with human values or religious belief, which have been expunged from modern physical science. That was his thing. These are all quotes from the Times of India interview, which you can read online. There's no video or anything. This is just an interview, I think, by email, where they question him on this. He also, by the way, said that he knew enough about the ancient texts to make these statements. So, well, these are his views. Take it or leave it. Now, here is an interview in which he was asked directly about his views on God. He says quite a lot of things. I've only picked a minute and a half, and this is a much older and bolder Weinberg, as you see, but very blunt and very clear about his beliefs. So please listen to it.
I do spend probably a little bit more time than I should on religion, and I have a certain amount of hostility to it. I think the most rational reason for it is because of the harm that I see it does. We were talking about that earlier. Many people do simply awful things out of sincere religious belief, not using religion as a cover, the way Saddam Hussein may have done, but really because they believe that this is what God wants them to do. Going all the way back to Abraham being willing to sacrifice Isaac because God told him to do that. Putting God ahead of humanity is a terrible thing.
Okay, so that was Weinberg on religion. Let's move on to Weinberg on a experimental collider project called the Superconducting Super Collider, or SSC. This was to be a particle collider proposed right from the 70s in the United States. The idea was that it would be built and it would go online sometime in the 1990s. It was to reach energies of 20 TeV, which is 3 times higher than the projected at that time energy of the Large Hadron Collider, which is running in Geneva at CERN, and which is the place where the Higgs boson was found. And this was where actually the idea was to build this first. It was a different design and technology. And the idea was, and it was much bigger, much bigger. And it was actually to be built in Texas. And the idea was for this to detect the things that the LHC has detected till now, and even more and much earlier. Now, in the 1990s, there was vigorous debate on whether the US government should fund it. I'll tell you an amusing fact. The funding was supposed to be a few $1 billion at that time. And India was the only country out of 7 partners which officially committed $50 million. It's mentioned in the literature on SSC that India committed this money, but as we'll see, the project didn't go ahead, so India didn't have to give. India saved that $50 million. But whatever. This debate was going on, and you remember at the opening of this talk, he's being interviewed by, I forgot his name, and that person actually in the full interview, which you can see on YouTube, he actually talks very optimistically, because that interview is in 1990. He talks optimistically on this collider, which is likely to be built. And he fought very hard in its favor. He wrote articles, he gave talks, he debated against both politicians and other physicists, including fellow Nobel laureate Philip Anderson, who himself opposed it. Now, physicists opposed it for their reasons, which is mostly they were condensed matter physicists who felt this is too much money to spend on one branch of physics, which they didn't find interesting. Politicians, of course, were thinking of other things, as you'll see in a moment. It was more about what the benefit is to them. Weinberg was invited to testify to US Congress, to the parliament there, and he spoke strongly in favor of the SSC. But he did not succeed. The SSC project was cancelled in 1993, and he became quite bitter after that. In fact, he became pessimistic about getting any future accelerator funded, given the political situation surrounding cancellation of the SSC. Here is Weinberg at the New York Science Festival about 6 years ago, and you can hear him talking about his pessimism and the whole, and a brief recap of the history, just a couple of minutes.
And my pessimism comes partly from my experience with another large accelerator project, which was canceled by a vote in the House of Representatives in 1993. This was an accelerator called the Superconducting Super Collider, and I'm going to abbreviate that to SSC. The SSC would have been even bigger than the Large Hadron Collider, a 53-mile circumference, and it would have accelerated particles to 3 times the energy that can be reached at the LHC. And it would already have answered these questions that we're hoping to see answered by the LHC. We struggled to get it funded. About $1 billion was spent on it, and then it was killed, as I said, by a vote in the House of Representatives. One thing I learned during the fight to get the SSC built was that no scientific discovery is remotely as important to a legislator as the economic interests of his or her own constituents. And this is not something evil. This is the way democracy is supposed to work. Legislators are supposed to represent the interests of their constituents. The problem is that it all too often turns out to be the short-term interests, and they don't provide enough wisdom and guidance so that their constituents will respond to the long-term needs. not only of their own little district, but of society in general.
Okay, so that was Weinberg on the SSC. And I'm now come to the last topic, and then we'll close. So I think I'm just in time. In 2016, now Weinberg had moved to Texas. It's difficult for Indians to appreciate the big difference between Texas and Massachusetts, but it's very big. The US, as you know, had slavery, and it was the southern states like Texas which strongly supported it, and the northern states like Massachusetts which opposed it. So politically, there's always been a big divide between these states. And the right to carry guns is considered very sacred part of the US Constitution. And somehow it's considered like an expression of the personal freedom of Americans. And it was already, of course, legal. You have to have a license everywhere, but it was legal to carry guns everywhere in Texas, but campuses were an exception. And even when campuses were allowed, classrooms were an exception. And actually, even till today, laboratories are an exception. You can't carry a gun to a lab. Okay, I think you can't carry a gun to an office, but you can carry it to a classroom. Now, these are details of US law, which I can't understand. But in 2016, the law gave college students the legal right to carry guns to classrooms. And at this time, and also the law even said that nobody can even ask a student if they are carrying a gun. The student can have the gun on their body, in their pocket or in their holster somewhere hidden, and you can't ask the student, against the law, to ask the student that question. And Weinberg, rightly, in my opinion, became frightened at the thought that he could be teaching to students who had guns, especially considering his views on God, which I just shared with you a few minutes ago. He actually says that sometimes when he gave these views in class, students angrily, one or two students angrily walked out of class. So he said it would be scary if that student had a gun. Who knows what would happen? So then this became a big newspaper and media event. Nobel Prize winning Texas professor says guns not welcome in my class. And I read about this in 2016 when it was happening, because I like to keep track of this kind of news. And so what Weinberg said was he was opposed to the law, and he says, I will put it into my syllabus that the class is not open to students carrying guns. But some students opposed that. There was a group of students, a pro-gun group of students. Some right-wing commentators wrote to the local newspapers like this one, saying he should be fired from his job. This is a Nobel laureate, Steven Weinberg. And the university did not support him. They basically said, look, it's the law. You would be violating the law if you say this in your syllabus, so you can't do it. Now, I don't know later how it was resolved. I don't know. I didn't know Weinberg personally, and there's not much news after that. Probably he taught small classes of 20-25 students, and he taught astrophysics, and probably they didn't bring guns and of their own choice. That's how I think it got solved. Okay, good. So I'll close with a few quotes, and then once a 1-minute summary again by Weinberg of what he believed in. So he said the following thing: we don't know what the LHC is going to find. If we did know, we wouldn't have to build it. It's a very nice quote. He said scientific theories cannot be deduced by purely mathematical reasoning. So though he himself worked actively in string theory during the 80s and wrote very important papers, which I studied, at the same time, he was uncomfortable that the theory didn't have any experiments that could be used to confirm or deny it. And so eventually he moved away from that to cosmology, where experiments were flowing in like anything. On the importance of pure science, he said this about J.J. Thomson, who discovered the electron. He says, if in 1897 he had been directed to work on practical problems, he would have developed a better steam boiler. As it turned out, he instead discovered the electron, which changed the universe, changed the world for the better. Some more quotes. This was very strongly said in that New York talk, which I showed you an excerpt. The International Space Station was sold as a scientific research laboratory. It has produced nothing of scientific value. His point here, by the way, is that experiments in space are important, but they don't need any human being to go up to a space station. They can be just controlled from Earth. The whole idea of sending human beings up to a space station or to the moon or to a planet is just kind of for popularity of the project, but not for the scientific value of the project. And he said this very strongly. In fact, partly it was this International Space Station which took away the funding from his SSC. Because this space station was also controlled from Houston, Texas. So it was seen like we are giving two big projects to Texas. And he said that Bill Clinton just didn't agree to that. Then he says on climate change, he says, it is generally foolish to bet against the judgments of science. And in this case of climate change, where the planet is at stake, it is insane to bet against science. So that's his view on climate change. Then he says, whatever the final laws of nature may be, there is no reason to suppose that they are designed to make physicists happy. And again, I think this was slightly a comment about very mathematical approaches based on beauty, though he himself has advocated it. He felt that it could be taken too far. Okay, and now I'll leave you with a final word, and I won't say anything more after that. This is Weinberg summarizing his talk at the World Science Festival in New York 6 years ago very beautifully.
What we need is for those of us who care about government support for all the things our society needs to unite, to help shift the balance of our economy more away from private goods in the direction of public goods, where the real needs of our society are. The real needs of our society are not for more consumer electronics, but for education, healthcare, scientific research, and so on. And this means higher taxes, which is a hard sell in a time when an anti-tax mania has afflicted the American public. But it's only in this way that we can get adequate funding for all the things that our society really needs, for education, for healthcare, for infrastructure, and all the others, and also for science of all sizes. Thank you.
Thank you very much.
Thank you, Professor Sunil Mukhi. That was a very interesting talk. So we have few questions in YouTube and in chat window here. So shall I read the questions?
If it's here in this chat, I can read it. So one is George Joseph asked, can I give an explanation of what symmetry means in physics? So actually it means two things. One, it means that one situation and another situation which appear to be different are actually related or equivalent. For example, rotational symmetry says that if I'm pointing in this direction or this direction or that direction or that direction, the laws of physics will be exactly the same. Now, you would say that it's not so. For example, this direction is my computer, that direction is my wall. Okay, but these symmetries are supposed to hold in the absence of everything. So in an absolutely in empty space, there's no way to know which way you are pointing. That is rotational symmetry. You can also move from one place in empty space to another. That's translational symmetry. Okay, gauge symmetry is a little bit more complicated because it says that the same situation can be described by different functions. For example, the vector and scalar potential in electromagnetism are not unique. The same electric and magnetic fields can be described by different functions, A and phi, the vector and scalar potential. So that's another kind of symmetry. Question on what is technicolor theory. Let me just say in one line, this was actually proposed by Weinberg also. It was a way out in case the Higgs particle is not seen. It was a way to, it was a model in which the Higgs particle itself, the particle which plays that role of creating spontaneous symmetry breaking and so on, is played by not a fundamental particle, but by a bound state of other particles. So that was so-called technicolor theory, and that theory got, I think, reasonably ruled out, and finally the Higgs particle was found. So yeah, cosmological constant is a term in Einstein's equations, which gives a constant energy density of empty space. It's quite remarkable because normally you would think that empty space has no energy, or you would think that empty space, the energy of empty space is up to you. You can just set it to 0 as a calibration, as a starting of your scale. But in gravity, that doesn't work. Empty space can have a energy, and there is such a thing as vacuum energy. And in fact, energy is not strictly conserved in general relativity. It's much more complicated than that. So the cosmological constant is a number which governs the amount of vacuum energy density per unit volume of the universe. And the amount at this time is whatever number I told you. Axions, Shaunak asked why axions are called a good candidate for dark matter. Well, dark matter is a form of matter which is not interacting by any of the conventional forces. Okay, it can't be charged, otherwise we would be seeing it, right? If there's a big charge distribution, then light would interact with it. Dark means light is interacting, not interacting with it through electromagnetism, nor anything is interacting through strong or weak interactions, only gravitation. Everything has to interact via gravitation. There are no exceptions. So that's dark matter. But axions were proposed for a different reason, to solve this strong CP problem. But maybe it's the same particle which solves the strong CP problem and also accounts for dark matter. That would make the theory more economical. So people like that very much. How many times physicists take inspiration, this is Yash, or argue for and against the philosophical ideas like Weinberg did with cosmological constant, especially in matters involving very fundamental theories and fundamental degrees of freedom. Some philosophy will come in. And cosmological constant and anthropic principle is still hotly discussed. Actually, it's discussed much more after Weinberg's paper of 1987 than it ever was before. Okay. Thank you, Rajshekhar, for your kind comment. Weinberg's view of the future of string theory, I don't know exactly what he said about it. I know that he worked on it. I know that he never said he disbelieves it. His main point was that for science to make good progress, you have to keep close contact with experimental facts. Now, the reality is that any theory of quantum gravity, not string theory, but any theory, will have predictions which can be seen by experiments at the Planck scale, which is a very, very small scale, 10 to the minus 33 centimeters. But there are no experiments possible in the present day at that scale. In the future, there might be. So in a way, the debate about string theory is not whether we should be doing it, but whether we should be doing it now, or we should do it at the time when experiments become available to probe that scale. And this debate, you see, you can never settle in the physics community because people want to work on what makes them curious. And their view is, well, we'll do some things, and then if experimenters are able to do the experiment, good. And if not, they'll do it after my lifetime. But I would like to contribute my thoughts, theoretical ideas on the subject. So I don't think Weinberg would disagree with any of the things I just said. I think it's a matter of open debate, but he was very, very strongly in favor of unification of all forces. And he actually did a very important work which showed that at energies of about 10 to the 14 or 15 GeV, which is completely out of range of the present experiments. In fact, it's close to the quantum gravity scale. He showed that the coupling constants of electromagnetic weak and strong forces can unify at that scale. This is a famous result of Georgi, Quinn, and Weinberg. And it's one of his, it's still a prediction for that scale. So he himself has a prediction for something that will happen at a scale out of reach of experiment. I think his problem was not with string theory, but with the amount of it that people are doing, like how much of the scientific community, how many are doing it. And, he feels that probably, or he felt that there are many observational problems, especially from cosmology, which people could be better off doing. Yeah.
So we have a question from YouTube.
Okay.
Ms. Shiba would like to know what the standard model is about.
Yeah. Okay. So the standard model has two meanings. The limited meaning is actually it's the model which was given by Weinberg under the name model of leptons. It's the electroweak theory. So it's a quantum field theory where every known particle has a field. So leptons, each one, electron has a field, muon has a field. Then the force carriers like W bosons, Z bosons have fields, photon has a field, and quarks also have fields. That was added later. And then the electromagnetic and weak interactions among these particles, leptons and quarks, can be calculated using those equations. And then those calculations give you the scattering cross-section, for example, of electron hitting another electron, or positron, or muon decaying, all the probabilities, the quantum probabilities, which we can measure. These equations determine those things, and you can compare between theory and experiment. So this is what the standard model originally meant. But there was one important force missing, which was the strong nuclear force. At the time of Weinberg's 67 paper, people were not quite sure what to do with that force because it was very strong. It turned out within a few years that there was a way to reformulate that force and to use it particularly when quarks interact at very short distances. That force effectively becomes weak. That weakness led to a possible theory, which is called quantum chromodynamics, which was developed basically due to the papers of Gross, Wilczek, and Politzer. And this theory can be just added to the Weinberg's, Glashow, Salam, Weinberg's model, and that makes the bigger standard model, which has both strong and weak and electromagnetic, all three interactions. But in that model, electromagnetic and weak are unified. Strong interactions are not unified. They're just there, separate. Okay. They also have their own force carriers called gluons. So that's the standard model. It's a theory, which means it's a set of equations which give you rules how to calculate all quantum processes involving all fundamental particles that interact via electromagnetism, strong or weak interaction. But you can't calculate gravitational interaction using that theory. It doesn't work. That's why people use string theory. Somebody here is asking repeatedly to explain what is dark matter. Okay. So observations of the universe show us that there are many places where the movement of galaxies, galaxies there are spiral galaxies, they rotate and so on. Now the speed of motion of objects in the sky is determined by the matter distribution because it's all through gravitational interactions. Okay. So you should be able to correlate the behavior of any object with the gravitational field of some other object nearby. For example, if the moon suddenly moved out of orbit, it would have to be because some other matter distribution which was close enough and with enough mass was deviating it from the orbit. There are no other ways because the theory of classical gravity is well established and no deviations have ever been seen. That's also why we are confident that moon will not move out of its orbit. Okay. So, however, observations of galaxies since many decades, many decades in the last century have shown that there must be some matter which we haven't accounted for. Now, how do we account for matter? By the fact that light from stars and galaxies gets reflected or bent by this matter, scattered by this matter. So we can see it. When we look in the sky and see a star, it's giving off light. If we see a planet, then it's reflecting light. So we see things by their interaction with light. What if, however, there's something which interacts only gravitationally? It doesn't interact through electromagnetism. It doesn't interact through weak and strong interaction. Such matter is possible. And it turns out that if we don't have that, then we can't account for the motion of galaxies. Okay, so we need to assume that there's a form of matter which is not any of the particles in the standard model. Because all the particles in the standard model do interact either by weak or strong or electromagnetic interactions or all three. Quarks, for example, undergo all three. Neutrinos only undergo weak interactions. Okay, photons only undergo electromagnetic interactions. So, but everybody undergoes one of these three. Dark matter would be one more type of particle which doesn't undergo any of these interactions. Okay? And it's proposed, otherwise we don't have any explanation why galaxies are moving the way they are seen to be moving. And the consensus is that not only there is dark matter, but it's a large fraction. It's much more than the ordinary matter. The visible matter is less, dark matter is actually much more. The visible matter is only 3 or 4% of the universe. Dark matter is more like 20 or 25%. But we don't know what it's made of. It could be related to any of the proposed new particles that were proposed for other reasons, like supersymmetric particles or like axions. Okay, that's the end of the questions so far, looks like. Also almost out of time, but I'm here if you have a few more questions, I don't mind.
Okay, Dr. Pradeep Desai is asking, is theory of relativity challenged by present-day physicists?
No, actually, nobody has challenged it. It's absolutely correct as far as all experiments are concerned. But it does break down in the presence of acceleration. So special theory of relativity was only proposed to take account of uniformly moving frames or absence of gravity. Now, general theory of relativity is, of course, the one which probably the question was about general theory. When we say theory of relativity, usually we mean special theory. General theory, which is the theory of gravitation, this theory also accounts for all known experiments. And just to give you one, when you open the GPS on your mobile phone, the calculation done by your phone when receiving the signal from a satellite and telling you where you are has corrections due to general theory of relativity. Without that, over a few days, it would build up an error of few kilometers. So you would try to go to some place like a restaurant, and you would end up few kilometers away from there, and then GPS is completely useless. If it can't localize you within few meters of your objective, it's useless. So general theory is being tested by you, all of you, every day from the fact that your GPS actually works. Now, people will always keep challenging every theory, and we always like those challenges. It's not that scientists don't like the challenge, but no credible challenge has been mounted as yet. And that's the statement. There's no cause to worry that general theory is wrong. There are people who work on it, and they should work on it. Okay. Antimatter is part of the standard model. So it was discovered originally by Dirac, who proposed it, that if there's a particle in nature which has an electric charge, there should be another particle with the opposite electric charge, such that the two of them can annihilate or destroy each other, giving rise to only light. So positron is the antimatter of electron. And when an electron hits a positron, the pair, both of them disappear and photons are emitted. It's not that the energy disappears, it's emitted in the form of photons.
Okay, I think the last question from Deepanvita Mukherjee on YouTube. Sir, could you please explain what is black body radiation?
Oh, black body radiation, I see. Black body radiation is nothing to do with my talk, though. I never mentioned black body radiation. If you really want, I can explain it. Whenever any object is hot, it radiates light. This we know. You know that iron can be red hot. If you heat iron even more, it becomes white hot. The sun also is white hot. We see that it looks white. But the simple fact is that even if you have something that is slightly warm, like I don't know, your cup of tea, even that is radiating light. The only problem is that it's not at the frequency which your eyes can see. Okay, so all bodies at any temperature are radiating electromagnetic radiation. Now, the question is, how much radiation of each frequency are they radiating as a function of temperature? It's a very simple question. Now, in general, we don't know, because if you have your teacup or coffee cup, it's irregular shaped, it might be radiating different amount in different directions and so on. We're not interested in those things. We are interested in an ideal object which is hot. And such an ideal object is called a black body. Actually, black bodies don't exist. They are just ideal objects. So in the idealization, I imagine that I have some region with a temperature. And now from that region, electromagnetic radiation is emitted, and I can calculate, this is what Planck did to give his radiation law, how much light will come out, what is the intensity of light between this frequency and this frequency, or between this and this frequency, how much will come out blue, how much will be red, how much will be green, how much will be infrared, which we can't see, ultraviolet, which we also can't see. Almost all of light we can't see, by the way. Yeah. Yes. Can gravitational lensing of nearby stars distort the light from distant stars? Yes. Hence, distant stars will not be visible on Earth. Yes, that's true. And that's also one of the ways we try to talk about dark matter, because that also contributes to lensing. It's not that the distant stars are not visible, they get distorted. So, for example, if there's one star, you should see one dot in the sky, but sometimes you see a ring of some like bright spots. And those are the gravitationally lensed version of that star. So we can always see those and realize that there's a star in the distance whose light has been distorted by the nearby stars. It's a very important tool for studying astrophysical objects, because we can't go there. So we have to study it from Earth, and gravitational lensing is a very useful tool because it gives that characteristic distortion pattern.
So I think we are almost time. So thank you very much for a very interesting and very engaging talk.
Okay, great. Thank you very much, all of you, and thanks for coming, and thanks for inviting me. Yeah, I'll leave now. Okay, bye.
Thank you all. We'll stop now.